So as promised, let's revisit this Wisdom Bridge problem for the most general case when there is a current flowing between point C and D, in which the bridge is not balanced. What we want to know is what is the equivalent resistance of this setup between points A and B. Now, again, since the bridge is not balanced, we cannot generally simplify this circuit into with a series of connections in parallel or in series. So we're going to start from scratch. We're going to go back to the very basic definition of resistance. We want to find the equivalent resistance between points A and B. So if you were to do an experiment to determine that, what would you do? Well, you would connect these 2 points A and B with a battery, right? And then let's say the battery provides EMF epsilon, and as a result you find a current I flows through the battery from point A to point B, and then by definition R equivalent would then be epsilon over I. That's how we define R equivalent. Okay, so what we need to do then is, given this battery with EMF epsilon, how does one find I? If I can find I, then I can find R equivalent, right? Now the question is, how do we find I? And again, the way to do that is to use the two Kirchhoff's rules. The first one, the node rule, and the second one, the loop rule. What does the node rule tell us? Well, if you look at point A, for example, we got a current coming in like this, and it splits two ways outwards. One is I1, the other is I3. So what can we say about point A, about this juncture, this node with the node rule? Well, the incoming current is I, the outgoing current is the sum of I1 and I3, so I should be equal to I1 plus I3, right? This is what the node rule says about point A. So if I can find I1 and I3, add them together, I get I. Plug in here, I will get R equivalent. So next, let's try to find I1 and I3. We need to continue to apply the node rule and the loop rule. So this current I1 flows through to point point C, at which point it's going to split two ways. One is it's going to pick up I2 from here to there, and there is another path going from C to D. Now, in fact, we're not quite sure whether the current in R5 is from C to D or from D to C. Okay? It can be either way, depending on the values of R1, R2, R3, and R4. We don't really know. Okay? But not to worry. All we have to do is to make sure we make a self-consistent assumption. The key word here is self-consistency. Now, suppose we designate a direction for the current flowing in this branch. We say it is from C to D. Okay? We call this I5. Right? We call this I5. So we assumed that the current flows outwards from at the node C. This is our assumption. I don't know if it's right or wrong, but that doesn't matter. What we want to make sure is we maintain self-consistency. And what does that mean? It means that since we believe that I5 flows out of the node at point C, we want to make sure that I2 plus I5, which is the net current flowing out, must equal to the current flowing in, which is I1. Okay, this is how I maintain self-consistency. So I have I1 equals I2 plus I5. Okay, if I define I1 to be flowing upwards, then this rule will have to be rewritten, because now I got two branches coming in and only one branch coming out. Then I would have I1 plus I5 equal to I2. See, I have to be self-consistent. Okay, now, meanwhile, let's look at what happens at point D. At point D, you got two currents going in, right? One is from here, I3, another one is from there, I5. So you got two incoming currents, I3 plus I5. Add them together, what do you get? You should get the current flowing outwards, which is I4. Okay, so this is the node rule applied to point A. This one is applied to point C, and the last one is applied to point D. Okay. Now, what can we say about point B if we apply the node rule? Well, I have here I2 and I4, right? These are the two currents going into point B, so I2 plus I4. and the current going out is just I, right? It's just I, which is just I1 plus I3. Agree? Okay, so we got 4 equations. 1, 2, 3, 4. The first one, we're not going to use that directly until at the very end when we figure out I1 and I3, add them together, we plug in here. Okay, so what's left? You got 3 more equations. We call this equation 1, and this equation 2, and this equation 3. All these are applications of the node rule. But are these equations all independent of each other? Obviously, these two are. Okay, but look at the last one. Applied at point B. Is this really independent of the first two? Well, see what happens if you add these two equations up. Okay, on the left hand side you get I1 plus I3 plus I5, right? The right hand side you would have I2 plus I4 plus I5. Both sides would have an I5, and if you cancel them out, you will find that I1 plus I3 equals I4 plus I2. But you see, that is just a third equation. Okay, so we do realize that this last equation is not independent. We don't need it. But on the other hand, it's also comforting to know that this last equation is actually consistent with the first two. Otherwise, if there's a contradiction, then something would be wrong. Okay, so we don't really need that. Sometimes we will get redundancy, just you can see from this example. But at least they're self-consistent. Now, those were the node rules. Okay. Now, what about the second of the Kirchhoff's rule, the loop rule? Okay, we can take any self-enclosed loop, such as this big loop, like here, such as this loop, such as this loop, such as this loop, such as this loop, such as this loop. Any self-enclosed loop would do. Okay, so you have a whole bunch of loops, but if you write an equation for each of these loops, all the possible loops, you'll find there are a lot of redundancy. You don't really need that many equations, do you? All you need is to solve for I1 and I3. See, right now we have I1 through I5, right, from these two equations, and that's 5 unknowns, I1 through I5, so we would need 3 more equations, okay, 3 more equations to finish this up. So let's see how we get 3 independent equations from the loop rule. Okay, let's, for example, take the parameter of the loop. That is one possible choice for the enclosed loop. I start from here. Okay, let me start from here, from this, and going clockwise. Going from here to there, I encounter an epsilon. So that lifts the potential up, epsilon. And then I arrive at point A. At that point, I move on to point C, following the direction of the current. So the current, when you go through a resistor following the direction of the current, what happens to the potential? It drops, right? Because the current flows from higher to lower potential. The potential drops by how much? Ohm's law, I1 R1. Then you arrive at point C. From here, you want to move on to point B, and again, the voltage will drop, the potential will drop from point C to point B by how much? By I2 R2. So negative sign because the potential drops. You will then arrive at point B. Once you arrive at point B, you go back to yourself. So this is 0. Okay, the sum of the change in potential as you go around the big parameter is 0. Now that is equation number 4. Okay, forget about equation 3. It doesn't work. Well, it's nothing new. And then that is only one parameter. Now how about this parameter? Okay, how about this loop? Well, this loop, I again start from here, epsilon. This time I'm going to take minus I3R3, right? So minus I3R3. Okay, and then minus what? I4R4. I4R4. That is also equal to 0. Okay, that is equation number 5. You see, I already have 2 equations out of the loop rule. I need 1 more equation so that I will have enough equation to solve everything. Okay, now you notice that at this point I have not used R5. Obviously R5 should be part of the solution to the problem. So let me choose a loop which includes point C to D. Okay, now how would I do that? You know, I can choose something like this. I can choose something like that, or you can even choose this or this. It doesn't matter what I do. Okay, you will not get the exact same looking equation, but a lot of these equations will eventually be redundant, as you see here. So let me just pick up arbitrary loop which contains this branch from C to D. Okay, how do I do that? Well, let's say I'm going to let's make a decision. Let's pick up this triangular loop starting from whatever point. Let's say starting from point C. Okay, I start from point C, I go clockwise until I go back to point C on this triangle. Alright, so let's do that. Starting from point C, going from C to B, what happens to the potential? Does it increase or decrease? Well, you follow the direction of a current going through a resistor. The potential should go from high to low, so it goes down by how much? By I2 R2. This negative sign means the potential drops. Okay, now careful, careful, careful. Once you're at point B, you want to go to point D, right? That's the next segment of this loop. But in going from point B to point D, you are going against the current. You see that? You're going against the current. Now the current always flows from high potential to low potential through a battery. Through a resistor. So this is the higher potential, and that is the lower potential terminal. And therefore, as you go from point B to point D, okay, what happens to the potential? Does it go up or down? It actually goes up, right, from negative to positive. So it's plus. Okay, careful, because you're going against the current. Plus I4 R4, right? That brings you to point D. You're gonna go back to point C. Once again, you're going against the current. Eh? You're going against the current. So therefore, what happens to the potential? It actually goes up, right? So because this is a negative terminal, that is a positive terminal. So plus I5 R5. That brings you to point C. So the net change again is 0. Okay. So you got 6 equations, but the third one is redundant. These 3 are not. Okay. So all in all, you have 5 effective independent equations. Okay. 1, 2, 3, 4, 5. And what you have to do is solve for I1, I2, I5. Okay. Now we're not going to solve it for you because of the lack of time, but you know it's quite simple to do, right? These are all linear equations. So especially when I give you some numbers, let's say this is 10 volts, this is 5 ohms, whatever, you can easily work out I1 through I5, all the numerical values. And once you get that, you don't need the rest of them. You only need I1 and I3. You add them together, plug in here, you get R equivalent. You see? So this is an example how we might calculate the electrical resistance of any complicated circuit without necessarily bringing them, simplifying them in series and parallel. And again, the key is to use Kirchhoff's rules. Okay, let's look at another example on the application of Kirchhoff's rules. This is what's called a multi-loop circuit. It looks quite simple. Okay, it looks quite simple, and yet there is no way. Okay, there is no way we can simplify this circuit into a simple combination of resistors in series and parallel. And the reason why is because you get 2 batteries, 2 EMFs belonging to different loops. Here's one loop, here's another loop. Okay? The only time you can simplify more than one EMF together is when you get EMF in parallel. Okay? Epsilon 1 and epsilon 2. If they're in the same direction, you add them together. If they oppose each other, you take one minus the other. That is how we might combine EMFs. But this time, it's not that simple. Epsilon 1 and epsilon 2, they're not in series, nor are they in parallel. Okay? So, we have a problem. You cannot simplify it into just series and parallel. But we don't need to, do we? We have a new way of doing things. We know how to apply Kirchhoff's rules. Okay, you're given all the R values, R1, R2, R3, R4, and 5. You're also given the EMFs of both of these batteries. So in principle, the currents in every branch of the circuit are predetermined. Okay, and our job is to find them. Let's find, for example, what is I1. Okay, and actually, I don't even know for sure whether the current flows from here to there. It might actually flow backwards if epsilon 2 is really strong. You can imagine, right? Because epsilon 2 encourages the current flowing backwards. So again, I'm going to make an assumption here. I assume that I1 flows this way. Okay. And by the way, how do you know whether assumption is right or wrong at the end of the day? Well, at the end of the day, you solve for I1 numerically. Okay. You solve for I1 numerically, and if I1 turns out to be positive, what does that tell you? It tells you our guess, our assumption, was actually correct. The current actually does flow this way. What if I1 is negative? It means we made a wrong guess. the actual current flows backwards. It doesn't really matter. We can always find the actual direction of the current as long as we're self-consistent once again. Alright, so let's apply the loop rule and the node rule. First of all, what happens at point A? You got a current I1 flowing in, right? And it splits two ways. One is I2. Actually, we call this I3. The other is I2. I'm assuming that the current flows like that in this branch. Okay? With that assumption, I have I1 equals I2 plus I3. Right? Okay. You can reapply the same node rule to point B and see what happens. This is I2, just like that. This is I3, and this is I1. And then you would be just getting I2 plus I3 equals I1, but just the same as that, okay? So, you don't have to do that. It's just, you get the same equation. It's again redundant. So, what about the second type of Herschel rule, the loop rule? Okay. There's the left loop, there is the right loop, and there is the parameter. Right? There are three types of loops that you can use. Again, I'm looking for I1, I2, and I3. I don't need three more equations. I only need two more equations. Okay, let's see if we can do that. Here is our first choice of the loop. We take the left loop. We can start from any point we want. Let's say we start from this point, going clockwise. Okay, we start from here, going clockwise. The first thing we encounter is this resistor, and the current is flowing along the direction of the loop, and therefore that will mean the potential will drop from here to there. So you go minus I1 R1. That brings you to point A. You could continue going down along the direction of the current. So once again, the current, the potential drops by I2 R2. That brings you to the positive terminal of this battery, and you're going from the positive to the negative terminal. That's how the path goes, and therefore you encounter yet again another drop in potential. So it's minus epsilon 2. Okay. This brings you to point B, at which point you keep on going. Okay, now be careful. You keep on going. This next time you're going to go through R5, and you're moving in the same direction as the current. So again, the current, the potential drops minus I1 R5. So the potential keeps on dropping all the time. But of course, it has to come back to itself. So at the very last stage of this loop, you go from negative to the positive terminal of the battery, and that is where you get a lift. Okay, the potential goes up by epsilon, and that brings you to the same point. So the net change adds up to 0. Right? That is the left loop. Now you can choose the parameter as a second loop, or you can choose the right one as the second loop. It doesn't matter what we do. Let's choose the right one, for example. Let's start from point A. You can start from any point you want. Okay, any point you want. Now, starting from point A, going through this resistor and this resistor with the same current I3. The potential drops here and it drops there. The net drop is negative I3 times R3 plus R4. Same current, okay? Which brings you to point B, at which point you keep on going. Okay, you keep on going up. So you go from negative to positive, so you get a lift. Okay, you get a lift in the potential, so it's plus epsilon 2, right? Okay, now that brings you to this point. Be careful. You have to keep on going up to reach point A, but as you keep on going up, you are going against the current, right? The current goes downwards, I2 goes downwards. As you go against the current, what happens to the potential? The potential goes up, right? Because the potential goes always from a positive, the current always flows from positive to negative potential. So potential goes up by how much? By I2R2. That brings you back to point A, so you get 0. Okay, so we got three equations. 1, 2, 3. Then you get three unknowns. Okay, I1, I2, and I3. Now, you can see what happens if you decide to choose the entire parameter of the circuit as a choice of the loop. If you did so, okay, you can start from any point. For example, you start this point, you go from to here, to here, to here, to here, to here. I want you to try this yourself, okay, and see what happens. Now imagine if you got an equation that is independent of these first three. Would this be a good thing or a bad thing? Well, we have three unknowns, I1 through I3, and we get three equations. That is perfect, right? But if you have a fourth equation, which has no new variables, just I1 through I3, right? Yet it's different from the first three, what does that tell you? You got too many equations, not enough unknowns. That is even worse than not having enough equations. If you don't have enough equations, the worst thing that can happen is that you have certain variables that you cannot figure out, right? But if you have too many equations and not enough unknowns, then it's even worse, because that would mean that there could be no solutions, because the equations could conflict with each other. Now, fortunately, this is not the case here. When you can see for yourself when you take a big loop like this. Okay, what you get is nothing new. What you get is an equation which is the same as the sum of these two, right? The sum of these two. Well, actually, let's do that. Let's not be too lazy. Let's actually do that. What happens when you add these up? Okay, when you add these up, you see a couple of things would actually cancel each other out. Negative epsilon 2, positive epsilon, that cancels out. Okay, and there's also a negative I1 R5, and there's a let's see what else. Okay, negative I2 R2. Here's positive I2 R2. You see, add them together, it cancels out. The rest do not cancel out. So add them together. Let's see what happens. Starting from this term, negative I1 R1. This term cancels with that term, so I'm not going to try. I'm going to write it. This one cancels with that one, so I'm not going to write it. This one I'm going to copy. Minus I1 R5 plus epsilon. That's that. And then minus this. So minus I3 R3 plus R4. That's 0. That's when you sum over these two, right? Let's see what this is. You know, this is nothing new, but the loop rule applied to the entire parameter. Can you see that? Okay, let's see. We start from here. We go all the way around like that. The first thing we encounter is a resistor R1, and we're going along the direction of the current. See, it drops by I1 R1. Next, we go to I1 R5. Where is that? That's okay. We sort of jump from here to there, but let's don't worry about it for now. Let's look at what should happen next. You go to this guy, so you should drop by I3 R3. See, negative I3 R3. Next, I3 R4 also drop. So that's that. That takes care of this term, this term, this term. And what you have left is now this guy and this guy. Okay, for this guy you have to drop by I1 R5. See, negative I1 R5. And for that one you should go up by epsilon. So you see that this equation really is the loop rule applied to the parameter. Okay, we're not getting anything new. We're getting something that's redundant but agreeable with these three equations. Okay, so the only thing that's left to do is to solve for I1, I2, and I3 from these equations, and that is left as an exercise. In fact, what we usually do is, we'll give you some real numbers, let's say 10 ohms or 2 volts, whatever. You can go ahead and solve numerically I1 through I5. These equations can be a little tedious to solve, but they're not hard to do at all. These are all linear equations. Okay, and linear equations can be solved with a special technique in linear algebra using matrices, and this is particularly suitable for a computer to solve. Okay, if you don't want to go through the tedious math yourself, computers are very good at solving linear equations because they can easily invert a matrix. So when you have any complicated DC circuit like that with any number of batteries, any number of loads like R1, R2, whatever, you can always apply Kirchhoff's rules to find all these currents. You may not only have I1 through I3, you may have 10, 12, or even 100 of these currents, but all you get is just 10, 12, 100 equations. All these are linear equations, and a computer can easily using the matrix method, can easily find the solutions. So in principle, with this Kirchhoff rules, we can find a solution to any linear circuit, any linear DC circuit.